And now going to part B. Part B says that we need to represent Z2. Z2 is given as negative 6i minus 6. That we need to find the principal arguments. So what do we do? Quickly draw your Gann diagram. This is the real part. This is the real axis of Z2. This is the imaginary axis of Z2. This is the origin 0. Now we have negative 6, which are equal in magnitude. So we are going to mark them equidistant from the origin. Equidistant. We are going to take the same. This is for real part, which is negative 6. So negative 6 is here, and the corresponding positive 6 is there. Then for the imaginary axis, also negative 6 is here, and the corresponding positive 6 is there. Now let us draw the complex number. Negative 6 and negative 6. That means on the real axis we have negative 6. On the imaginary axis we also have negative 6. So it is this negative 6 and this negative 6. So we just get a dotted line vertically down, horizontally to the right. Then this is where they are meeting. This is the point of intersection. So you get a ruler and join that point to the origin. Which will look like that. And then put an arrow on top. And then you can mark it and say this is my Z2. We have illustrated it on the Gann diagram. Now we need to get the argument, which is an angle measured from the positive x-axis, which is this side here. So the argument becomes from here up to where the complex number is. That is the argument. The whole of that angle is argument, and we call it theta. Now we need to now find the theta. But if you see, moving from here up to here is 180 degrees. That means we already have 180 degrees. Let me partition it. This side is 90 degrees and this side is 90 degrees. That gives us a total of 180 degrees. But now we don't know what this angle is, this small angle. So that we add it to 180 to give us the argument. So what do? We need to extrude this triangle from here up to here, and back there. So if you look in this format, I will have that. I have dotted line here vertically straight, which you can draw as solid lines, and then I have the complex number, which is in that format. That means this idea forms the right angle triangle. 90 degrees is there. That is where 90 degrees falls. Now this is where your angle is. This is the angle we are looking for. You can call it anything. You can call it A, B, C, or anything you want. For now, let me call it alpha. Alpha. Now, from here up to there is negative 6. From here up to there is negative 6. But we are going to put 6. The negative just shows the direction, which is on this side. But the units are 6. And then from here up to here, we don't know it. This is the length of the complex number, which we have not got. And then from here up to there, from here up to here, is the same as from origin up to negative 6. But we're going to take it as 6 units because the sign just shows where it is falling in the 4 quadrants. Remember, this is the first quadrant, second quadrant, third quadrant, and then this is the 4th quadrant. Now that we have this, we have extracted the information we have from there. Now, this is our angle called alpha. Opposite to the angle is 6, which we are calling opposite now. The longest side is always the hypotenuse, which is not given. And then the side which is adjacent to the angle is the adjacent. So after getting that, then you apply your cutoff. So cutoff. Now, if you are to use sine, that means you need opposite and hypotenuse, but here you don't have the hypotenuse. If you want to use that, that means you must go ahead and first find the hypotenuse. The same to cosine. You need adjacent and hypotenuse, but hypotenuse is not there. You first need to find it. But if you look at tan uses opposite and adjacent, which we have opposite and adjacent. So there you don't need to waste time. So we now say therefore tan, I've called the angle alpha, is given by opposite out of adjacent to the angle. That means here now tan of alpha is going to be opposite to the angle is 6 and adjacent to the angle is also 6, which is 1. 6 divided by 6 is 1. So tan of alpha equals to 1. If I'm looking now for alpha, I will say now alpha, which is my angle, becomes tan inverse of 1. Then we press the calculator. Tan inverse of 1, 45. This gives us a 45 degrees. Now we have got alpha 45 degrees, which is just this small angle, which was this. Now when we are now finding our argument, which we are calling theta, the argument now becomes this small angle 45 degrees plus this other obvious side, which is 180 degrees, which we partition into 90. Then you add plus 180 degrees. This gives us here 25 degrees. This is just the argument which we have measured from the positive x-axis. If you look into this range, 225 is out of the range. 225 is outside the range. So this is just an argument. This is just the argument. But now to get the principal argument. For the principal argument, we just need to get a value of the angle which lies in this range. Since this one is bigger, we need to now measure it clockwise, so that we get a small angle we can fit in this range. Now, we already have 225, and the whole circle has 360 degrees. That means for us to get this portion that we can measure clockwise, we need to just say 360 minus 225. That gives us 135 degrees. But we are going to say it is negative. Why? Because we are taking it clockwise. So therefore here now the principal argument Z2, which is R to Z2, it becomes 135 degrees. But we are going to indicate the negative. Why? To show that we are measuring it clockwise, which is now in this range. Negative 135 is bigger than negative 180, so it's tending towards the positive 180 degrees. So this is the principal argument and this is the argument. This one is anti-clockwise. This is measured clockwise. But at this stage, there is no penalty when we ask you for the principal argument and we give you answer as argument. It will be marked because we are not very strict here. We are giving you the foundation of complex numbers. So this is the solution to part B. Let us go to part C.